Welcome back to Physics 192. I'm Gerard Blanchard. Last time we introduced the concept of power in alternating current circuits, and our equation for power in alternating current circuits is power is equal to delta voltage RMS times current RMS times the cosine of the phase angle between the voltage and the current, or power P is equal to delta V RMS times I RMS times cosine of phi. And we use delta V RMS and I RMS, each of which is 1 over root 2 of their respective peak values. So I RMS is equal to 1 over root 2 times I max, for example. And we do that to simplify the equation for power. If we didn't, we'd have another factor of a half in the power equation. But just to make things more similar to what we already know, that is that power is equal to voltage times current, we use the RMS values. So that power is delta V RMS times I RMS times cosine of phi. Let's work on some examples. An RLC circuit is connected to an AC power supply with a 12-volt max amplitude and a frequency of 2.5 kilohertz. If R is equal to 220 ohms and the capacitance is 8 microfarads and the inductance is 0.15 millihenries, what is the power dissipated? Go ahead and draw your circuit, and remember to convert the maximum voltage to the RMS voltage, and then you'll be able to use the equation I RMS is equal to delta V RMS over Z, the impedance. That equation holds for RMS current and voltage the same way that it holds for maximum current and voltage. Here's our circuit. There's our voltage delta V max is equal to 12 volts. The frequency is 2.5 kilohertz or 2,500 hertz. And we've connected it to an resistor, inductor, capacitor circuit. And the resistance is 220 ohms. That's R. R is equal to 220 ohms. The inductance is equal to 0.15 millihenries, or 0.15 times 10 to the minus 3 henries. And the capacitance is 8 microfarads, or I should rewrite that, 8 times 10 to the minus 6 farads. And we know that we're going to have to calculate X sub L, the inductive reactance and the capacitive reactance. X sub L is 2 pi FL, which is equal to 2 times pi times 2,500. That's 2.5 kilohertz. Times 0.15 times 10 to the minus 3. And we'll calculate that out in a second. Let's also do our X sub C. That's 1 over 2 pi FC, or 1 over 2 pi times 2,500 times 8 times 10 to the minus 6 farads. And what does that equal to? Okay, I'll calculate 2 pi FL first, or our inductive reactance. 2 times pi times 2,500 times the inductance of 0.15 times 10 to the minus 3 henries, and that gives us 2.36 ohms. 2.36 ohms. And the capacitive reactance is 1 divided by the quantity 2 times pi times 2,500 times the capacitance 8 times 10 to the minus 6, and that gives us a capacitive reactance of 7.96 ohms. 7.96 ohms. We should convert our voltage, maximum voltage, into RMS voltage. Delta V RMS is equal to delta V max divided by square root of 2. So that would be 12 over root 2. Our delta V RMS is equal to 12 divided by square root of 2. That would be 8.49 volts. So our RMS voltage is 8.49 volts. Now we have a current flowing in the circuit, IRMS. And we've gotten everything we can now out of the question statement, except what is it we're looking for? We're looking for power. We're looking for the power. We know that the power is equal to delta V RMS times I RMS times cosine of phi, the phase angle between the voltage and the current. So we'll have to figure out, we know delta V RMS, so we'll have to figure out I RMS and phi. So we figure out I RMS using I RMS is equal to delta V RMS divided by Z divided by the impedance. And as I said, this equation, you've seen it before as I max equals delta V max divided by Z. Well, the same relation holds for RMS because current and voltage are related to the maximum by the same factor of 1 over root 2. So that gives us I RMS is equal to 8.49 volts divided by Z. Z is the square root of R squared plus X sub L minus X sub C squared. Or I RMS is equal to 8.49 divided by the square root of R, which is 220 squared, plus X sub L, which is 2.36 minus 7.96, quantity squared, and now we just have to calculate I RMS is equal to 8.49 divided by the square root of 220 squared plus the quantity 2.36 minus 7.96, and that quantity is squared. So let's just double check. We have 8.49 divided by the square root of 220 squared plus 2.36 minus 7.96 squared, and that gives us 0.0386 basic metric units of current, which are amperes. So that is our RMS current. Let's get our phase angle. So we've got delta V RMS, I RMS. Now we need phi. Phi is equal to tan inverse of x sub L minus x sub C divided by R. R phi is equal to the inverse tangent of 2.36 minus 7.96 divided by 220, which gives us phi is equal to the inverse tangent of the quantity 2.36 minus 7.96 divided by 220, which gives us a phase angle of negative 1.46 degrees. So that's our phase angle. And now we have everything we need to calculate power. Power is equal to delta V RMS 8.49 times I RMS 0.0386 times the cosine of negative 1.46 degrees. So the power is equal to 8.49 times 0.0386 times the cosine of negative 1.46, and that gives us 0.328. 0.328 watts. Basic metric unit of power is the watts. So 0.328 watts, and that is what we were asked to find. Let's work another example. The wiring circuit for a typical room is shown schematically in the diagram. There is a 20 amp RMS circuit breaker in the circuit at D. The RMS voltage of the hot wire is 120 volts. Suppose the heater draws 1500 watts, the lamp draws 300 watts, and the microwave draws 1200 watts. What is the RMS current that would flow through the circuit breaker if all of the appliances are operated simultaneously? And you may assume that the phase angle is 0 for all of the appliances. So the phase angle is 0. So we'll have cosine of 0 in all of our power terms. Please try to work this one. Here's our circuit diagram. Here's our power supply. Delta V RMS is equal to 120 volts. So that's the whatever supplying power to your home. This is grounded, so that's 0 volts down here. And we have a heater. And the power to the heater is equal to 1,500 watts. And the heater is plugged into both of the wires. Then we have a lamp. Power to the lamp is 300 watts. And we have a microwave. Power to the microwave is 1,200 watts. Okay, and then there is a circuit breaker right here, and that was A. Okay, Now when each of these is plugged in, some current flows from the hot wire to the neutral wire. And so that would be I heater, I lamp, and I microwave. And all three of these join up to flow through the circuit breaker. So the current at the circuit breaker is equal to I heater plus I lamp plus I microwave. So all of that current comes from the outlet, from your electrical outlet, and returns to your electrical outlet after flowing through these different appliances. Well, we know delta V across both of these, and we are looking for the current, and we know the power. We know delta V and we know the power, so we can use the relationship, the power of the heater is equal to delta V RMS times IH RMS. And the power to the lamp is equal to delta V RMS times I lamp RMS. And the power to the microwave is delta V times I microwave, delta V RMS times I microwave RMS. And what happened to my cosine of phi? Well, for all of these, cosine of phi is equal to cosine of 0 degrees, which is 1. So there's an implicit times 1 in all of these, but I don't have to write that since times 1 doesn't change anything. Okay, so the power to the heater is 1500. Delta V RMS is 120 times I heater RMS. So 1500 divided by 120 is equal to I heater RMS. And I'll go ahead and do that for the other ones as well. The power to the lamp is 300, and that's going to be equal to 120 times I lamp RMS. So 300 over 120 is equal to I lamp RMS. The power to the microwave is 1200 is equal to 120 times I microwave RMS. So 1200 over 120 is equal to I microwave RMS. And I can see right away that 1200 divided by 120 is going to be 10 amperes, is going to be I microwave RMS. So let's calculate I heater and I lamp. I heater is 1500 divided by 120. That would be 12.5 amperes. And 300 divided by 120 is 2.5 amperes. Okay. The current, I RMS, is equal to I heater RMS plus I lamp RMS plus I microwave RMS. So I RMS is equal to 12.5 plus 2.5 plus 10. Our I RMS at the circuit breaker is 12.5 and 2.5 is 15, so that'd be 25 amperes. So if we were to run all three of these appliances at the same time, the current at the circuit breaker would be 25 amperes, and the circuit breaker is rated for 20 amperes, so turning on all three of these appliances at the same time would trip the circuit breaker. And in fact, you can see that even the heater and the microwave running at the same time would trip the circuit breaker. So you can only run the heater or the microwave, and you could run either of these with the lamp. So you can run the heater and the lamp, or the microwave and the lamp, but you can't run the heater and the microwave at the same time, or you'll have to reset your circuit breaker. Let's work one more example. In her bathroom, Mindy has an overhead heater that consists of a coiled wire made of nichrome that gets hot when turned on. The wire has a diameter of 0.85 millimeters and a length of 3.0 meters if it were uncoiled. The heating element is attached to the normal 120 volt RMS wiring and produces 2,200 watts of heat. Nichrome has a resistivity of 108 times 10 to the minus 8 ohm meters at 20 degrees Celsius and a temperature coefficient of resistivity of 0.0004 inverse degrees Celsius. So the first question is, what is the resistance of the wire? And once we do that, there's a second question, and that is, what is the temperature of the heater when it is turned on? Now, to answer that question, you'll have to recall some relations that we had earlier, and that is the resistance of a piece of wire is the resistivity, rho, of the material times the length of the wire divided by the cross-sectional area of the wire. And the area would be pi r squared, where r would be is the radius of the wire. And the resistivity itself is temperature dependent. Resistivity is equal to resistivity 0, that would be the resistivity at 20 degrees Celsius, times the quantity 1 plus alpha times the quantity T minus 20 degrees Celsius, where alpha is the temperature coefficient of resistivity. So first, what is the resistivity of the wire? Let's draw our circuit. This is delta V RMS is equal to 120 volts, and that's connected simply to a resistor, which is just a bunch of wire, and the length of the wire, L, is equal to 3 meters. The diameter of the wire is equal to 0.85 millimeters, or 0.85 times 10 to the minus 3 meters. The resistance, we don't know. We'll have to find that out. That's what we're looking for. And the current, IRMS, we also don't know. We do know, however, that the power is equal to 2,200 watts of power. And we also know that the wire is made up of a material that has a rho 0, or a resistivity at 20 degrees, of 108 times 10 to the minus 8 ohm meters, and a temperature coefficient of resistivity of 0.0004 degrees Celsius inverse, or per degree Celsius. And we were given the relationships. Resistance is equal to rho times L over the area of the wire, where rho is equal to rho 0 times 1 plus alpha times T minus 20 degrees Celsius. And I'll just leave it like that. Okay. We don't know the temperature, so we don't know the resistivity. We don't know the resistivity, we don't know the resistance from these equations. So we can't use these equations to calculate the resistance. We'll have to use the power and the voltage to figure that out. How do we do that? Power is equal to delta V RMS times I RMS times the cosine of phi. We know that the power is 2200. We know that delta V RMS is 120. We don't know I RMS. That's an unknown. And we know, since all we have here is a resistor, we know that the phase angle is going to be 0 degrees. The phase angle is 0 degrees for a resistor. Okay. Well, we can solve this for I RMS, and that would be 2200 divided by 120 divided by the cosine of 0 divided by 1, so I don't really have to write that, is equal to I RMS. And that tells us that I RMS is equal to 2200 divided by 120, or 18.3 amperes. That gives us the current. And now that we know the voltage and the current, we can calculate the resistance, because I RMS is equal to delta V RMS divided by the impedance, but since we only have a resistor, the impedance is equal to the resistance. We can multiply both sides by resistance, divide both sides by current, and we'll have resistance is equal to delta V RMS over I RMS, or the resistance is equal to 120 divided by 18.3. 120 divided by 18.3. And that tells us that the resistance is equal to 120 divided by 18.3, 6.56 ohms. So the resistance of this resistor is 6.56 ohms to give us that power when connected to that voltage. Now that we know the resistance, we can work backwards through these equations. If we know the resistance and we know the length of the wire and the area of the wire, then we can calculate the resistivity. And once we know the resistivity, we know rho 0 and A, and we can calculate T. So let's do that. R is equal to rho L over A, where R is 6.56 is equal to the resistivity times the length, which is 3 meters, divided by the cross-sectional area of the wire, which is pi, times the radius of the wire. The diameter of the wire is right here, 0.85 times 10 to the minus 3. Well, we'll have to divide that by 2. Actually, I'm going to need more space. 0.85 times 10 to the minus 3 divided by 2. There we go. Sorry, that's 0.85 times 10 to the minus 3 divided by 2. And we'll square that, and then we need to divide everything by that. Let's go ahead and calculate what 3 over pi r squared is. So 6.56 is equal to rho times 3 divided by the quantity pi times the quantity 0.85 times 10 to the minus 3, and then divided by 2, and then we're going to square that. And that comes out to be 5.29 times 10 to the 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Times 10 to the 6. So 6.56 divided by 5.29 times 10 to the 6 is the resistivity of the wire. So 6.56 divided by 5.29 times 10 to the 6 gives us a resistivity of 1.24 times 10 to the minus 6. Okay, so now that we've figured out the resistivity, we can use this equation right here to figure out the temperature. We know resistivity, resistivity 0, and the temperature coefficient of resistivity. So rho is equal to rho 0 times 1 plus alpha times t minus 20. Let's put in what we know. We have 1.24 times 10 to the minus 6. We're going to divide that by rho 0. So I'm going to divide both sides by rho 0. Actually, I'll go ahead and do that. I'll divide by rho 0. Rho 0 is 108 times 10 to the minus 8. So that is rho divided by rho 0. I've already taken the step of dividing by rho 0. That is equal to 1 plus alpha times t minus 20. That's what we have left over here. Let's do this division. 1.24 times 10 to the minus 6 divided by 108 times 10 to the minus 8. That gives me 1.15. 1.15 is equal to 1 plus alpha times t minus 20. So I'll subtract 1 from both sides. And I'll have 0.15 is equal to alpha times t minus 20. And then 0.15 is equal to alpha, which is 0.0004 times t minus 20. Or if I divide both sides by 0.0004, so 0.15 divided by 0.0004, that gives me 375 is equal to t minus 20. So 375 plus 20 would be 395 equals T. So we were able to figure out the temperature of the wire when the heater was operating. The last thing that we have to talk about for alternating current circuits is resonance. Resonance is a special situation where the inductive reactance is equal to the capacitive reactance. The inductive reactance is 2 pi times the frequency times the inductance, and the capacitive reactance is 1 over 2 pi times the frequency times the capacitance. So for a given inductance, L, and a different capacitance, C, the inductive reactance increases with frequency and the capacitive reactance decreases with frequency. So there has to be one frequency at which those are the same. We can solve this equation for the frequency. We can multiply both sides by the frequency and divide both sides by 2 pi L, and that gives us the frequency squared, the resonant frequency squared, is 1 divided by the quantity 2 pi squared times the inductance times the capacitance, or the resonant frequency is 1 divided by 2 pi times the square root of L times C. So there is always a frequency at which the inductive reactance and the capacitive reactance are the same. Now, when the inductive reactance and the capacitive reactance are the same, the capacitor and the inductor cancel each other's effects out. So at resonance, the impedance of a circuit is equal to just the resistance, and the phase angle is equal to 0, because the phase angle is the inverse tangent of XL minus XC. So when those are the same, divided by R. So when XL and XC are the same, we have the inverse tangent of 0, which is 0. So when we have Z equals to R and the phase angle equal to 0, that is when we get the greatest possible current in our circuit and also the greatest possible power in our circuit. So that's what's special about the resonance. That's when we get the greatest current in the circuit and the greatest power. And for a given inductor and a given capacitor, there is always a single resonant frequency. Let's work an example. An RLC series circuit has an inductance of 0.3 henries and a capacitance of 6 microfarads. The source has a peak voltage of 440 volts. What is the resonant frequency? When the source is set at the resonant frequency, the peak current in the circuit is 0.56 amperes. What is the resistance in the circuit? So go ahead and draw your diagram. Find the resonant frequency from the inductance and the capacitance, and then find the resistance of the circuit from the voltage and the peak current. Here's our diagram. There's our source, and here's our resistance, our resistor, our inductor, and our capacitor. And this is delta V max is equal to 440 volts. The frequency is the resonant frequency, which we're going to find. The inductance, L, is equal to 0.3 henries. The capacitance is equal to 6 times 10 to the minus 6 farads, or 6 microfarads. The resistance is unknown, and I max at the frequency, I max at resonance is equal to 0.56 amperes. Okay, what is the resonant frequency? The resonant frequency is 1 over 2 pi times the square root of L times C. So the resonant frequency is 1 over 2 pi times the square root of 0.3 times 6 times 10, let me do my parentheses, 6 times 10 to the minus 6. So the resonant frequency is 1 divided by 2 times pi times the square root of 0.3 times 6 times 10 to the minus 6. And that gives us a resonant frequency of 119 hertz. So that is the resonant frequency. And we're told at the resonant frequency that I max is equal to delta V max divided by R, because the inductive reactance and the capacitive reactance cancel each other out. So the impedance is equal to just the resistance. I max is 0.56 amperes. Delta V max is 440 divided by R. That tells us that R is equal to 440 divided by 0.56, or the resistance in the circuit is 440 divided by 0.56, and that would be 786 ohms. So the resistance in the circuit is 786 ohms. Well, that wraps things up for electrical circuits. Next time, we're going to start with nuclear physics. Until then, think physics.